All right. Accelerating AI training workloads with cloud TPUs and GPUs. Welcome, ladies and gentlemen. My name is Vaibhav Singh. I'm a product manager for cloud accelerators at Google Cloud. And joining me today, my esteemed co-presenters are Rob Martin, who is a senior engineering manager at Maloco, Amanpreet Singh, who is a co-founder and CTO at Contextual AI, and Erik, Nijkamp, who is a research scientist at Salesforce. And today, we are going to talk about why accelerators, what are the three key considerations when it comes to operationalizing accelerators at scale. That is performance, frameworks, and orchestration. And then we will learn from Maloco how they are powering their large-scale ranking and recommendation systems using cloud TPUs, followed by learning from Contextual how they are powering their retrieval-augmented generative models using cloud GPUs. And finally, we'll hear from Salesforce how they are using both cloud TPUs and GPUs to operationalize their large language models in production. With this, let's get started. If today we can dream about a teacher for every student, a doctor for every patient, this dream is only possible with AI at scale. And AI accelerators are foundational in realizing that dream. It is no secret that AI is generating tremendous value, and it is powered by AI accelerators at scale. However, when it comes to operationalizing AI accelerators, it can be often daunting, especially at scale. And at the same time, it presents a unique opportunity for optimizations and cost savings. And this is why we created AI Hypercomputer, which is a supercomputing architecture that brings system-level co-design across stack, beginning from performance-optimized hardware, bringing you the best of cloud TPUs, GPUs, or even CPUs, our storage and networking infrastructure, bringing the best-in-class open source software, powering our orchestration layer, the runtime, the frameworks, as well as reference implementation innovations to get you started as quickly as possible to the highest level of performance. And performance is one of the key topics of today, and we'll come to that in a little bit. And finally, flexible consumption models. That is to meet you where you are in terms of your unique accelerator needs in terms of timing and capacity. So in order for you to make the best of AI hypercomputer, here are the three key considerations that we are going to talk about today. The first is performance. When it comes to accelerators at scale, reasoning about performance, whether you're using cloud TPUs or GPUs or a combination of multiple accelerator generations, it's extremely important. Second is framework. Understanding what are the feature and focus of each framework enables you to make the right choices when it comes to making use of these accelerators. And last but not the least, orchestration and development, which are key to then make use of all these implementations and performance best practices. And we are going to talk about the toolings and the options available for orchestrations that will set you up for success. So let's begin with performance. When it comes to reasoning about performance, often it's tempting to look at an accelerator chip in isolation, to think about the peak theoretical flops or the peak memory bandwidth or the peak accelerator memory capacity. While relevant, it is often seen in practice that it is the performance of the system at scale that matters the most rather than a performance of a single chip. And when it comes to reasoning about the performance of a system, here are a few metrics that you should consider. The first is model flop utilization, also known as program goodput. And there is a talk tomorrow, which is ML productivity at scale. Please tune in to learn more about goodput and how you should try to optimize ML productivity at scale using some of the best practices. Coming back to model flop utilization or the program goodput. What is model flop utilization? It is the fraction of the peak theoretical flop of a system that your program is able to utilize. Notice the keyword utilization. It's not the peak flops. It is the utilized flop. So for instance, if your training cluster has a peak flop of 200 petaflops per second, but your training job can only utilize 100 petaflops per second or has a throughput of 100 petaflops per second, then your model flop utilization is 50%. When generalized to mixed precision settings, we call it effective model flop utilization. Going back to the same example, let's say you turn on mixed precision training and you were able to improve your step time by 20%. Thereby, your effective throughput has increased by 25%. So now you're effectively creating or generating the throughput of 125 petaflops in the same example. Thereby, your effective model flop utilization is 62.5%. Well, why does it matter? Because when you create or drive an effective performance per dollar, 25% more, you drive the cost down by 20%. And based on your training budget, this can be a significant number. So metric number one, effective model flop utilization. We need to know about that. The second is the scale. The question is at what scale? You can run a job at 8 or 16 chip scale and achieve a very impressive model flop utilization, but that is often not very useful. So scale is useful. Applying EMFU to scale, here is one example. Here we are showing some results for a 512 billion parameter dense decoder language model, which was implemented using MaxText on Cloud TPU v5p, which went GA today. So with v5p, we are able to generate or achieve up to 85% of effective model flop utilization. But that is not the point. The point is, as we scale this training to the twice or the 4 times or 8 times, up to 12 times the cluster size, we are able to sustain this utilization. And what it means is when you use this 12x more hardware, you can go close to 12x faster. That means that you can finish your work or accelerate your cycle time or time to market by 12x by paying a little or no premium. So that's the power of scaling. And what we presented here is what we call strong scaling analysis. That is taking the same workload and trying to measure the performance of this at increasing cluster sizes or a scale. And if your system does it properly, then it has the direct consequences or benefits or business advantage in terms of time to market. Very significant. So utilization is important. Utilization at increasing scale is also important. What is next is, you might wonder, so what if I need to train on larger and larger model sizes? That's a valid question, and that leads us to weak scaling. So when we look at the performance of a system, when we increase the model size with the cluster sizes, here we are showing the weak scaling characteristic with TPU v5p and v4. So as you see that both the red and the blue bars, or the blue curves there, they sustain or even go higher as we scale the model sizes from 64 billion parameter all the way to 1 trillion parameter dense decoder language models. What it means is that irrespective of the model size, or even if your model size is scaled, the system can actually scale in the proportionate manner so that you sustain the cost advantage. And what we are showing in this benchmark is Cloud TPU v5p was able to deliver up to 3x more performance per dollar in comparison to TPU v4. So to recap, utilization matters, utilization at scale for the same model matters, and utilization at scale for larger and larger models also matters, namely strong and the weak scaling. Now, consider this question. How to compare two infrastructure options? So far, we have learned that performance per dollar or the effective model flop utilization matters, and yes, indeed it does. So we consider performance per dollar. But is that enough? At what scale? Are we going to consider the same number of accelerator chips for the two systems? You may guess probably not, because they are vastly disparate in many, many respects. Then what we should indeed look into is what we call the useful work or the good put, introducing ISO good put analysis. So what this focuses on, to make this more concrete, is let's say you have a 1,000 parameter dense decoder language model to train on 1,000 tokens. So the total work the useful work that you need to do is approximately 6 million floating point operations. So that is the useful work. And when you consider the useful work, then you have a certain time, a target time for your training. Let's say you're trying to ship a model next month. So you have a job, a useful work, which is a certain number of floating point operations or a certain number of total work that needs to be done. The good put that needs to be delivered, and the solution that you want to choose is the one which can achieve this useful work or achieve the good put within a target training time at the lowest cost. So here are a few examples. And this is based on some simulated results comparing V4 and V5P for an internal model for a reference data set. And this is showing on the x-axis the training time, or the time we have to finish the job. And on the y-axis, we are showing throughput per dollar. And the red curve shows V5P, and the blue shows V4. Not very informative, you say, because you've already seen that V5P is demonstrably better at scale with V4, obviously. However, there are a few observations that we can take away from this chart. If we are on the right-hand side or on the rightmost extreme of this curve, the gap between the two curves is large enough that the choice is easy. We say V5P, hands down, let's just choose it and move on. But if you go to the leftmost extreme, since this is using the fixed global batch size, and as we move from the left to the right of the curve, we are using larger and larger system, and beyond a certain point, the throughput per dollar start to taper off for both of the systems. And if you are in leftmost system, you have 2 days to finish that work, then likely the difference between V4 and V5P is not that significant. So this means another dimension. The time to finish the useful work or the good put is also something that you should take into consideration. And here is one more example which will make a lot of sense for all of you who are also considering multi-slice and single slice uses. So the blue curve is showing you the ISO good put curve generated for a single slice scaling with TPU V5P. And the red curve is showing the scaling with multi-slice up to 8,192 chips, where the blue one only scales up to 6,144 chips. As I said earlier, as we move from right to the left or the left to the right, okay. So as we reduce the number of training days, we are using larger and larger systems, and therefore there is a region. If your training budget in this specific example for that model size and the data set that we used was 5 days or 10 days, hands down, you should use multi-slice V5P with likely 8,192, and you can scale even higher. And however, if it was 15 days or higher in this specific example, you're better off using a single slice system. So to recap, the utilization matters. The utilization at scale matters. The utilization at scale considering the training time that you have. This altogether combined resulting with ISO good put analysis is what gives you the insight of the accelerator that you need to choose. All right. So moving to our next consideration, that is frameworks. So when it comes to framework, there are two key aspects that we should think about. First is optionality, because it is true today that there are tremendous amount of opportunities that we can explore with AI accelerators, and we want to use both cloud TPUs and GPUs and hopefully be able to interoperate between them. So optionality is a North Star that we would like to facilitate and we would strive for. So second are reference implementations. So when it comes to achieving the best possible performance, the effective model flop utilization numbers that you saw, 85% and the likes, we have built reference implementations which can get you started and help you ramp to that as fast as possible. So these are the two dimensions of the frameworks and implementation that I will touch upon today. So begin with the optionality. So OpenXLA, or the XLA compiler that we a few months or maybe an year ago open sourced, creates a path to optionality. And what I'm showing here in this picture is that if PyTorch, JAX, or TensorFlow are using OpenXLA as the backend or the compiler, then the benefit is that it can generate code for both GPUs, TPUs, as well as a handful of other hardware options available. That means that it provides the path of flexibility. Additionally, you also benefit from out-of-the-box optimizations or a host of other scaling features which have been built into XLA for TPUs, and we are working very hard to bring in those features for GPUs as well to make this path of optionality more and more meaningful for you. And finally, now we also support expanding the capability of OpenXLA with custom kernels. And I think there is a talk on JAX, which will go into the details of Palace as the library that you can use to write your own custom kernels that you can use, work with both JAX as well as PyTorch. So something that we should look into. And finally, also notice that for all the 3 frameworks that we are showing on the top, we are generating or translating the computation into same intermediate representation. That means that if the computation is the same, then downstream optimizations is expected to produce very similar results. That translate to the same base or very similar baseline performance expectations. So here is an example. This is comparing Llama 270B pre-training benchmark on V5P that is comparing PyTorch XLA and a handful of other measurements using JAX. You will see in the red and the blue bar, they are very, very close. This means the baseline performance that we measured with PyTorch, XLA, and JAX was very, very similar. Where there are 2 additional bars there which are pushing this even further. So definitely there are features in JAX as framework for large-scale language models or even large-scale training in general, which are helping to achieve these gains. And that these features are point in time, work in progress for PyTorch XLA. However, in terms of the focus of PyTorch XLA and JAX, both the framework have a strong focus or the emphasis on facilitating or bringing in the best of the training performance. And similarly, one more example of that focus is TensorFlow, where we have the focus on ranking and recommendation workloads, where we have the TPU embedding API that can take advantage of the sparse core present on the TPU devices. And we'll hear from Rob how Maloco is powering their ranking recommendation systems, which is also taking advantage of the TPU embedding API in TensorFlow. So, and now moving to the second axis or the second aspect of framework, which is reference implementation. Based on which framework you have, we have built reference implementation to ramp you up as fast as possible to the best performance. For instance, MaxText, this is our reference implementation we built initially for Cloud TPU, and now it supports GPUs as well. So if your goal is to get to the state-of-the-art performance, to match or reproduce what we have measured in some of our benchmarks that we were also showing earlier, MaxText is the go-to library. You can adapt ideas into your own training implementations from these. Similarly, we have Max Diffusion that we very recently introduced, as well as TFRS. This is for the TensorFlow recommenders, as I was mentioning earlier. For PyTorch, we are partnering very closely with Hugging Face, and we are building first-class support for TPU as well as GPU using PyTorch. So, for example, a few months ago, we published Gemma. And with Gemma reference implementation in the Transformers library, you could use it off the shelf, ready to go with both Cloud TPUs as well as GPUs for your fine-tuning work, as well as Diffuser and PyTorch Lightning libraries, which are very well supported. And going forward, we will continue to work and drive these to more and more optimal points. And last but not the least, let's talk about the third consideration. That is orchestration. When it comes to orchestration, your teams can be opinionated. So this is why we have the full spectrum of orchestration choices, leading from the manual or fully self-managed to fully managed using Vertex AI, which can be further augmented with libraries such as Ray or weights and biases, and everything in between. But between is actually where the interest is, or the magic happens. You can augment your self-managed orchestration using Slurm or Ray. We will hear some examples of using Slurm with our A3 VMs today. And finally, the foundational orchestrator, which is built and optimized for scale, is using GKE. And the reason why I call it foundational is that this is the orchestration option that lends itself to the most extensibility using all the ecosystem tools available. And this is where we are continuously building all the features and functionalities for large-scale, reliable ML to bring the best possible goodput. So, and the reason why this is also so crucial is that this is open to allow you to bring your own ideas at work. So you are not limited by what we have shipped. You can easily augment and develop on it. Finally, when it comes to augmenting, we have done such augmentation work with GKE, and it is called Accelerated Processing Kit. This was published late last year, which is a simplification layer on top of GKE, which abstracts away the job set API, which is the abstraction that we have to express the large-scale ML workloads. And it also has features such as queue. Using Kubernetes queue, it also offers a way to maximally utilize resources. Now, multiple teams in your organizations can submit jobs using XPK to GKE. And these jobs can be queued with different priority levels, and that's why you can keep your accelerators occupied the most amount of time and thereby derive a lot of efficiency benefits. And the way it does it is using 2 simple nouns and 3 simple verbs, as I call it, using the cluster and workload, create, list, and delete APIs. Simple. You're no longer working with YAML file. You don't even know what job set syntax looks like. And this has been tested and widely used for our own internal resource sharing purposes for all the benchmarks that you have seen, as well as for our largest training job that we published last year with 50,000 V5E chips powering a single job. And this was orchestrated using XPK, and it has also been adopted by many of our customers. And we are very excited about the simplicity and yet power of XPK. And finally, HPC Toolkit. As I said in the beginning, that what are the tools and the options that you should know about? Contrary to the name, this is important for ML orchestration because this provides you a simple, repeatable way, a 3-step process where you can define what you need to provision in terms of your compute, storage, and networking. And it can, and this format is what we are calling blueprint. And HPC Toolkit can then translate this blueprint into the Terraform manifest as well as a set of scripts, which can then be used to provision your resources. We also publish out-of-the-box blueprints, which can be leveraged. This is the example of A3 VMs on Slurm, which can be used with HPC Toolkit. And there are similar blueprints for A3 VMs on GKE, as well as blueprints for Cloud TPU using Slurm. So with that, I'm going to pass it on to Rob, who is going to tell us about Maloco and how they're powering their large-scale ML with Cloud TPUs. Please help me welcome Rob.
Thank you. Thank you, Vaibhav. It's a real pleasure to be here today to discuss our journey together to onboard tensor processor units for our machine learning workloads at Maloco. So let me start by introducing Maloco. Maloco is a machine learning company. It's right in the name, actually. We produce machine learning powered solutions that help our customers monetize their platforms through performance advertising. So we did about $1 billion in ad sales last year. We grew about 8x in the last 3 years. We actually made Financial Times list of fastest growing 100 companies this year. And we're fairly small and lean and focused machine learning company. We're very eng heavy. About 40% of our workforce is either machine learning engineers or software engineers, a large percentage of whom have advanced degrees in computer science or mathematics. So if you were looking to build a machine learning company from the ground up, world-leading quality, it would look a lot like Maloco. So we actually use our machine learning solutions to power performance advertising solutions across multiple verticals. including retail, where we can offer targeted advertising within e-commerce platforms, within mobile, which is our biggest sector, where we power advertising within free-to-play games and social media apps that use that strategy for monetization. And our newest vertical that we're entering is streaming, where we're offering ad insertion into streams similar to what YouTube does. And all of this is possible because of our reliance on operational machine learning, which is a highly automated form of machine learning and allows us to power these solutions at really massive scale. So to give you an idea of the reach that we have with our systems on the open internet, we interact with multiple exchanges. We have access to multi-million applications in the app stores, and we're accessible via about 6 billion mobile devices all around the world. So, this slide describes how our business works in one slide. So let's say that perhaps you're playing your favorite casual game on your phone. Every so often, that game needs to monetize, and so it'll generate what's called a bid request. That bid request goes to an ad exchange where it's fanned out to multiple demand service providers such as Maloco. We take that bid request, select an ad inventory, choose a creative, price our bid, and then we send all that information back to the ad exchange. And if Maloco bids highest on that bid request, then we get to display that ad to that user. And that all has to happen in about 100 milliseconds. So, as you can imagine, when you only have 100 milliseconds to make those kind of complex decisions, traditional methods have relied on very fast and simple ways of making those decisions. Statistical methods, regressions, decision trees, etc. What set Maloco apart is that we chose to use more advanced techniques like deep neural networks to make those decisions, which allows us to offer more targeted solutions for our ad recommendations. So the way that we've been able to scale this up is by leveraging something that Vaibhav referred to as the operational side of machine learning. So whereas traditional machine learning might involve building models in notebooks and maybe occasionally promoting a model to production, with operational machine learning, the entire process is automated. All of our training is automated. All of the decisions are made in real time. And as you can imagine, the computational power to power all of that is really immense. So before we talk specifically about how we're using tensor processor units, I wanted to take you just through a brief journey in what we call Maloco Scale. So remember, we've got 6 billion devices that we're addressing every day. We receive about 600 billion requests every single day from those devices for ads. That's trillions of requests per month. So that equates to about 10 petabytes worth of data that we have to ingest every day. A lot of that data becomes training data for the next version of our models downstream. So we respond to all of those bid requests using deep neural networks, and we're pushing about 6 million QPS through TensorFlow and Kubernetes. And a lot of people think of Google search as a pretty busy place on the internet. That's only about 100,000 QPS by point of comparison. So remember, we only get 100 milliseconds to make all of those decisions. And it actually takes about 10 different deep neural networks to place a bid. There's a lot of different decisions that we have to make about selecting the right inventory and making the right bid, and there's a whole host of models that work together to make that decision. So that's what we have these large teams of machine learning engineers focused on. Now, what that means, though, is that the predictions coming out of any individual model is closer to 10 milliseconds than 100 milliseconds, which is about an order of magnitude faster than what's typically possible with deep neural networks. And to top it all off, we have to keep these models fresh because we're doing real-time bidding, responding to ever-changing market conditions. So we're retraining about 1,000 model instances every day. So how do TPUs fit into this picture? So you might be surprised to know that for most of Maloco's history, we've been training on CPUs. And you might think that's a little counterintuitive. But the reason that we've relied on CPUs is because they're cheap, they're readily available at scale, they're always being upgraded and enhanced with new capabilities. They work really well with GKE, Vaibhav mentioned that. And we can also scale these up into fleets of large, CPUs that we can use to train our models together. So we can string together more than just one CPU. So, that's worked pretty well for us for most of our lifetime. But recently, we found the need to go faster, introduce models more quickly, and also go bigger. And so we're looking at ML accelerators of various types. And Vaibhav alluded to many different attributes that you might evaluate when you're thinking about the right hardware for the right model. And it turns out that different models and different use cases have different hardware that's best fit. But we're really happy to be adding TPUs to the mix. So some of the things that specifically are useful to us are the multi-core heterogeneous core architecture of the TPUs. So Vaibhav mentioned the tensor cores and the sparse cores. And for recommender models, it's actually quite useful to have access to those two types of cores. We also really like the ability to take these hosts and scale them up as slices that have optical interconnects, so we can treat those as large virtual hosts. And so those characteristics of TPUs, pretty unique. So, it is a pretty giant leap to go from CPUs to TPUs. It's sort of like going from the family car straight to a Formula One car. So it's been a bit of a journey to retool our infrastructure so that it can take full advantage of those TPUs. So there's a number of different upgrades that we've had to go through that we've got here on the slide. But to close out, we've been really happy with the results that we've gotten from the TPUs. We've gotten faster training times, very important to us when we're introducing all those new models. We're seeing cheaper training costs, which is really great to get faster and cheaper at the same time. But on the challenges side, I don't want to undersell the complexity here. If you're going to drive a Formula One car, you have to be ready. You have to have the right kind of crew and the right kind of driver. So it is a technically complex upgrade process. You got to be comfortable living on the bleeding edge. But for Maloco, this has been a really great fit, and we're really happy to be partnered with Vaibhav and his team. So I will close out there, and I would love to welcome Amanpreet from Contextual AI, who will provide the next example. Please welcome him.
Hello, everyone. Thanks, Rob, for setting up the stage nicely for GPUs and showing us how powerful TPUs can be in general. So let's start with a brief intro of what Contextual AI does and what exactly we are doing. So at Contextual AI, we are building next generation of retrieval augmented models specifically for enterprises. So let's start with what are the challenges specifically when we are trying to make language models move into production. As we all know, ChatGPT has revolutionized the world in November 2022, but we still don't see a lot of AI in production. So what are the challenges that are preventing these language models from moving into production? Specifically, they hallucinate a lot. They say things that they didn't say in very specific use cases where it can be very bad depending on the use case specifically. They don't provide attribution of why they say and what they say. There is no audit trail. You can't trace it back on what data source actually led to this particular generation. There are data privacy issues. Customers don't want their data to be seen by other customers. You can't train on all of the data that is available. So you have to be very concerned about the privacy aspect there. Then you also have cost-quality trade-off. As we know, GPT-4 and Claude 3 have been awesome on coding and logic reasoning capabilities, but they're still very expensive if you deploy them in prod. Like if you actually deploy them at a scale, you will run out of money soon if you don't properly cache it and add a lot of layers on top, which leads to cost-quality trade-offs depending on your use case. You don't necessarily need an AGI model for those specific things. Finally, these models also get stale. As we saw in Maloco's use case, there are a lot of things happening every day in the stock market. These models are not aware about these things. And if you have compliance requirements, they can end up being losing the compliance things because they are outdated requirements. Everything keeps on updating every day. So you have to make sure these models update with time and achieve the compliance requirements. So one solution there is RAG, Retrieval Augmented Generation, which my co-founder Dao Akila came up with when he was at Meta with me. So what happens in Retrieval Augmented Generation is you have a document encoder which is used to feed into a vector database, which you can use to retrieve relevant chunks later based on semantic similarity. So query is encoded, you fetch the data from the vector DB, you attach a LLM to it, and you hope everything works out. So that's how RAG generally works in production systems. So we internally call this Frankenstein because there are a lot of moving parts here that are joined together through prompt engineering or a lot of other techniques to make it work. But in reality, a lot of companies or a lot of enterprises are stuck in demo mode. When they try to deploy it, there are a lot of things that go wrong. It's hard to maintain. Every new use case that comes in, you have to hand tune it. So it does work, but it's sort of very custom and like hand tuned. So they don't actually work together if a little bit of change happens in the use case. So this is where RAG 2.0 comes, which is our proprietary technology. So what we do is we train the retriever and the language model together with each other for the end use case, and we optimize for the end use case specifically. So RAG 2.0 beats GPT-4 RAG-based model out of the box on specific RAG benchmarks, which actually capture the 5 problems we discussed initially, which are preventing the enterprises from moving into production. So on hallucination, freshness, and few other topics, RAG 2.0 beats even GPT-4 when it's combined with RAG there. So RAG 2 also improves over time. So as you know, like if you, as we talked about, if you use RAG plus GPT-4 and you add a lot of custom tuning, prompt engineering on top, there is a limit to how much you can achieve there. And the model stops improving with time. So, but RAG 2.0 with custom specialization and feedback continues improving over time for that specific use case, eventually meeting the production bar. So RAG 2.0 is specifically designed for enterprises and making sure like it actually improves as you keep on using it. So it becomes your proprietary technology as well. So coming back to the point, like we have done a lot of research breakthroughs in the last year since we came out of stealth from June 23rd. So all of this, including KTO, Lens, Grit, these are foundation technologies that lead us to make RAG 2.0 eventually in March. And they are all powered by our GCP A3 cluster. So we have a huge cluster which we use for like training workloads, and we have been very supported by the GCP team in making sure the scale that we are trying to achieve with research has been achieved. So how do we do this? So we have talked about a few of these things initially. So our cluster is powered by H100s, where we get all of the improvements from the latest technology of GPUs. And we use Slum through HPC Toolkit because our researchers are usually well-versed with Slum through their different experiences, and it's very easy to use. So that's the second layer that we use for orchestration. Then on top of it, the solutions, the storage matters a lot, because if your GPUs are idling because of storage, you need to make sure that it's not bottlenecked by storage. So we benchmarked a lot of them, and we ended up with choosing Weka because the performance per price dollar was like most optimal for the Weka solution. Then we actually implement our own custom PyTorch-based distributed training framework because we wanted to encapsulate all of the best practices from our years of experience in the research into the framework. So developers and researchers both get optimal experience out of the box. Finally, the custom policies for best developer experience so that there is a shared, consistent environment, and we make sure like everything works out of the box really well for these developers. Finally, we talked about ISO good put, but how do you actually achieve it in production or in research clusters? It's not just about training velocity, it's also about cluster velocity, like how fast you can, if your nodes are actually down, if your cluster is down, you anyway can't train, so your ISO good put will go very low. So you want to make sure like node replacement, auto cleanup, a bunch of other things are in your system already by day one. Then you also want to make sure that even if your nodes are up, that your developers are not sitting idle because they can't move fast, which means your GPUs are sitting idle and you're wasting money. So you want to make sure that the framework that you're using is really good, less opinionated, modular, and has a lot of shared scripts which can be used across developers and build a common knowledge source so they can move faster. Finally, last but not the least, the training velocity is the most important thing. So pay attention to the interconnect that you're using, the storage that you're using, and 3D parallelism to get most out of your training cluster. With this, I will hand over to Erik, who will talk more about how they use TPUs and GPUs at Salesforce. Thank you.
Right. I've been told to be quick, so let's be quick. I'm Erik. I'm at Salesforce Research. I'm pre-training LLMs for 2 years now. And these slides will tell you how can you pre-train competitive LLMs with only 2 engineers, with a very small team? Today we are larger, but 2 years ago we were only 2 researchers. Right, so let's dive right in. Salesforce research has been around for 10 years. We have been pushing predictive and generative AI for quite a while. In aggregate, Salesforce is delivering 1 trillion predictions per week. And if you look at these highlighted models, Cogen, Progen, Cogen 2, and XGen, these are the open source pre-trained LLMs Salesforce is delivering on TPU. Let's dive right into these. So Cogen 1, that was 2 years ago, we trained on TPU v4, and at that point in time, it was OpenAI Codex competitive, and one of the largest open source models with 16 billion parameters. Later on, we followed up with Progen 2, which instead of trained on code is trained on proteins, one of the largest open source models for protein modeling. And today we're training XGen models, which are generic foundational models on text. All of these models are powered by JAX-Former, that's our in-house JAX library, and most importantly, trained on TPUs. So the entire stack of models is trained on JAX-Former on TPUs with a very small team. So how do you achieve this? How can you train all these models if you only have a very small team in generative AI? Let's look at these challenges and solutions quickly. Right, so the challenges you already know. You need data, you need flops, and you need engineering on a very high level. If you deep dive further, you need flops, that's the compute. You need the orchestration of the compute. You need a reliable cluster. You need the model implementation itself. Once you have the model, you need to partition the model parameters over the cluster to get efficient training, that's scaling. And then lastly, you want to have highly efficient forward and backward passes for MFU, like we discussed earlier. So if you only have a small team, how can you deliver all of this? Yes, you can deliver it if you stand off the shoulder of giants, like Google in this case. So small team, good hardware, good software, partnership with Google, and yes, this works. So again, JAX-Former is our in-house pre-training library, obviously based on JAX, as the name says. So how we're training our models, if you go bottom to top, flops and orchestration, we're using TPU v4 cluster, which has very low failure rate per chip. So that's solving the problem. Then the model implementation is based on Haiku, Flex, and Optics abstractions, which we have on top of JAX. Once you have these models implemented, you can do data and model parallelism with native first-class citizens, primitives, and JAX. So it's very simple to partition your model across the compute cluster. And then more recently, you can actually lower custom kernels, like we elaborated earlier, into XLA for specific kernels like Flash, if you want to get long sequence support, or block sparse kernels if you want to support a mix of experts. And what's impressive, so if you have this relatively simple engineering stack up and running, say in 3 months on 1024 v4 chips, you can train a competitive 30 billion parameter model. So with a small engineering team with the stack and the amount of compute, it's quite competitive. Right, so what's next? We're looking forward for TPU v5p. Mega blocks, which are block sparse kernels for a mix of experts. Splash, which we already tried. Here you have efficient patterns over your attention kernel, say for sliding windows. And we are looking at a max text, which is one of the reference implementations and has high MFU, which you can use to train your models on TPU. That's pretty much it from Salesforce research. I'm handing over back to Google.